Welcome, everyone. Today, we are transforming dense theoretical wave formulas into an absolute masterclass on Cambridge exam methodology. We are not just reading a textbook today, we are stepping directly into the shoes of a Cambridge senior examiner. Imagine you are a film director, and your exam paper is your script. You want to build a blockbuster answer, right? You need to cut the filler, keep the action, and deliver exactly what the audience, or in this case, the examiner, wants to see. To understand how to do this, let's look at two completely different types of students. On one side of our split screen, we have Alex. Now, Alex is a seriously hardworking student taking the Cambridge physics paper. When Alex sees a question on progressive waves, what happens? Absolute information overload. Alex dumps every single raw physics fact onto the page. We're talking a total brain dump, but absolutely zero analysis. It's like a movie with too many special effects and no plot. On the other side, we have Sam. Sam is constantly rushing through the paper, frantically racing against the clock. Because of this rush, Sam entirely misses the specific command word requirements hidden right there in the question. The tragic result for both of them? A massive sea of red pen marks across their exam papers. Today, we are going to fix that. We are going to build your blockbuster answer, scene by scene. We are going to show you exactly how to master progressive waves, maximize your mark potential, and leave those red pen marks in the dust. Let's get right into it.
Now, take a look at this quote on the screen. This validates exactly why we are analyzing these principal examiner reports today. Every single year, thousands upon thousands of students walk into their physics exams feeling totally confident about progressive waves. They've spent hours memorizing the formulas, they know the definitions back to front. But then, when the results come out, they are completely stunned. They've lost so many easy marks. Why does this happen? Well, as our side-by-side comparison of Alex and Sam perfectly illustrates, Cambridge examiners are definitely not looking for a robotic regurgitation of facts. Think about Alex. Alex wrote down every single wave property known to humanity. But Alex failed to apply any of that knowledge to the specific context of the question. And Sam? Sam jumps straight into a complex calculation without defining the parameters first, completely ignoring the command word explain. Listen, the red ink on their papers isn't because they don't know the physics, it is because they don't know the game. This explainer right here is your ultimate cheat code to that game. We are going to dissect the exact anatomy of a perfect answer, showing you how to satisfy the examiner's deepest, strictest requirements without breaking a sweat.
We've put together a clear, highly structured roadmap to get you your target grade today. We'll be moving from theory to execution to avoiding those common pitfalls. Part 1 is the foundation, Part 2 is the framework, and Part 3 covers the traps. Let's keep moving. Let's start with the theoretical architecture required by the Cambridge syllabus. Here is Section 1, the foundation. Okay, let's break this down. The formulas on screen are the bedrock. Intensity equals power over area, and intensity is directly proportional to the amplitude squared. Sounds incredibly simple, right? But this is exactly where students like Alex completely derail their entire exam. The crucial point is that while these formulas are fundamental, rote memorization alone will never, ever secure you the top marks. Before we continue, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Now, back to our strategy. The syllabus specifically states that the theoretical architecture of progressive waves rests on precise definitions and causal relationships. It is simply not enough to just write I equals P over A and hope for the best. You need to deeply understand the physics assessment objectives. You need a rock-solid strategy. In our system, we use the PIL framework. That stands for point, evidence, explanation, and link. Let's say a Cambridge question asks you to explain the effect on intensity when the amplitude of a progressive wave is doubled. Your point is stating the relationship clearly. Your evidence is the mathematical proportionality, showing that I is proportional to A squared. Your explanation is detailing exactly how a factor of 2 in amplitude results in a factor 4 in intensity. And finally, your link brings the entire answer right back to the specific physical wave mentioned in the prompt, whether that's sound, light, or a water wave. Think back to our two students, Alex and Sam. Which of them used the PIL framework? Absolutely neither of them. And that is exactly why their mark potential is stuck at a lower grade boundary. This brilliantly illustrates what top-performing candidates do differently. They demonstrate a connected, conceptual understanding. When you look at the principal examiner reports, they highlight an absolutely incredible insight. Candidates who actively reference cross-topic connections achieve significantly higher marks. What does this actually mean for you? It means if you can elegantly link the intensity of a progressive wave to concepts of energy transfer from kinematics or even wave-particle duality later in the syllabus, you instantly elevate your response from just average to truly
exceptional. The examiners explicitly state that top-performing students exhibit an understanding that is transferable to entirely unfamiliar contexts. This is huge. It means when they throw a completely bizarre scenario at you on exam day, like, I don't know, measuring the intensity of seismic waves traveling through an unknown planetary core, you don't freeze up and panic. You rely on these 4 pillars on the screen. You define your terms precisely, you establish the causal relationship between power, area, and amplitude, and you apply your framework fearlessly, no matter how weird the context seems.
Let's move to our next section and see how this theory actually builds into an actionable, procedural framework for your answers. This is section 2, the framework.
Listen closely, because this is where we initiate the real transformation. Examiners heavily reward what we call the method-mark strategy. This means your evidence-based reasoning is just as important, if not more important, than your final calculation. Imagine watching those brutal red pen marks on Alex and Sam's papers magically transforming into beautiful green check marks. How do we actually do this? By introducing the Physics Success Blueprint. In Cambridge Physics, you absolutely do not just get points for writing down the final correct number at the bottom of the page. You are awarded marks for the process of systematic analysis. Let's say you make a tiny calculator error at the very end of a massive calculation, but your procedural framework was absolutely flawless. You extracted the data from texts and tables correctly, you interpreted the theoretical relationship between intensity and amplitude properly, and you drew logical, evidence-based conclusions. If you do all that, you will still scoop up the vast majority of the marks for that question. The method-mark strategy dictates that your working out is essentially a story. It's a logical narrative proving to the examiner that you didn't just guess the answer, but you mathematically and conceptually derived it step by step. This is exactly why cutting the filler and keeping the action in your written response is so vital to your success.
So whenever you tackle a complex physics problem, you must apply this precise, deconstruct, solve, evaluate methodology to absolutely guarantee you get those method marks. Let's walk through it. Step 1 is deconstruct. You read the question and you immediately identify the given information. You pull out the data. You ask yourself, what is the power here? What is the cross-sectional area? Step 2 is solve. You break the massive problem into logical, manageable steps. You apply the analytical framework we just discussed. For example, if the area is circular, you physically write down the calculation for pi r squared. You then substitute this into your I equals P over A formula. Don't skip steps in your head. Step 3 is evaluate. This is the ultimate hallmark of a top-tier candidate. You stop and check for reasonableness. Does an intensity of 10,000 watts per square meter make any logical sense for a gentle, quiet sound wave? Probably not. You evaluate your numbers and you justify your findings based on the physics. This 3-step process is your ultimate shield against the silly, careless mistakes that constantly plague rushing students like Sam. It literally forces you to slow down, analyze the scene, and execute with absolute cinematic precision.
Now, data interpretation is critical, but examiners demand strict adherence to specific presentation conventions. You could honestly have the most brilliant, Nobel Prize-worthy physical insight in the world, but if your presentation on the exam paper is a mess, the examiner literally cannot give you the mark. Clear annotation, appropriate formats using the correct terminology like saying displacement instead of just distance moved, and using proper headings are completely non-negotiable. Presentation isn't just about having nice, neat handwriting. It is about communicating efficiently in the universal language of physics. If a question asks you to plot a graph to show the relationship between intensity and amplitude, your axes must be clearly labeled with the correct units. The curve you draw must be smooth, demonstrating that I is proportional to A squared. That means it needs to be a parabolic relationship, definitely not a straight line. These are the strict conventions that separate the decent students from the truly A-star candidates.
Let's dive into the climax of our explainer. We are looking at the specific traps and warnings pulled directly from examiner reports. This is section 3, the traps. But wait, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's uncover these critical examiner alerts. According to the data, there are exactly 3 major mistakes that consistently cost students their method marks. We're going into an interactive workshop right now. I want you to imagine a 60-second timer on the screen. Let's do a rapid-fire mental exercise. Imagine a complex physics data source flashing right in front of you. It's a dense chart showing wave intensity dropping dramatically over a specific distance. 60 seconds on the clock. You're scanning that data. What is the core trend jumping out at you? Think about it.
It's telling you that as the wave spreads out radially from a point source, the area it covers increases massively. Because intensity is power over area, the intensity naturally drops. This is the famous inverse square law in action. If you cannot spot that trend quickly during your initial scan, it means your methodology is vulnerable to the 3 examiner traps we are about to reveal. Your ability to instantly process visual and tabular data under time pressure is exactly what keeps you out of these traps. The crucial point to understand here is that failing to link your knowledge to the specific context given in the exam is the ultimate mark killer. Let's go to challenge number 2, find the flaw. I'm going to read a flawed sample paragraph written by Sam. I want you to find the sentence that is losing marks. Listen closely. The intensity of the wave increases because it is proportional to the amplitude squared and energy is transferred along the wave. Okay, spot the flaw. The examiner commentary here would be absolutely brutal. Sam's answer falls right into trap number 3, providing generic, memorized answers. Sam's sentence is theoretically true in a vacuum, but it is completely devoid of context. What wave is Sam talking about? Increased by exactly how much? Trap number 1 is using the wrong approach for the specific context, and trap number 2, which we just covered, is forgetting those vital presentation conventions. The classic heartbreaking mistake across the board is regurgitating a perfect textbook definition without ever once linking it to the unique scenario the examiner has spent hours crafting for you. You must always connect every single point you make back to the given scenario.
Let's jump to challenge number 3, speed writing. We are going to build a perfect PEL paragraph right now. Let's look at the scenario. A water wave's amplitude is reduced by half as it passes through a narrow gap. Explain the effect on the wave's intensity. A generic, poorly thought out answer would just say, intensity drops because amplitude drops. That gets 0 marks. Notice the binary difference when we build a context-specific PEL structured answer. Here we go. Point. The intensity of the water wave decreases. Evidence. This is because intensity is directly proportional to the square of the amplitude. Explanation. Since the amplitude is halved, or decreased by a factor of 2, the intensity is reduced by a factor of 2 squared, meaning it becomes exactly 1/4 of its original value. Link. Therefore, the energy transferred per unit area by the water wave through the narrow gap is significantly diminished. Wow, that right there is a blockbuster answer. That is exactly how you turn a dry theoretical relationship into a concrete, undeniable sweep of maximum marks.
Top-scoring candidates constantly question assumptions and justify their recommendations using this exact evaluative framework. Imagine a progress bar on your screen tracking your mark potential. By implementing what we've discussed today, that bar is finally reaching 100%. To consistently master these higher-order assessment objectives, you need to lock in the 3 rules that guarantee top marks. Rule 1, command word decoding. You must never, ever answer a complex discuss question with a simple one-word state response. Rule 2, PEL framework application. We have definitively proven how point, evidence, explanation, and link force your brain to be context-specific. Rule 3, the time management matrix. Do not be like Sam, rushing blindly and missing critical details. Pace yourself using the deconstruct, solve, evaluate method. When a tough question asks you to problem-solve an unfamiliar wave scenario, you must critically evaluate the alternatives, compare different approaches, and above all else, justify every single decision with hard mathematical and physical evidence. This descriptive, analytical, and evaluative layering is the true hallmark of Cambridge excellence. As we wrap up this explainer, I really want you to evaluate your own study habits. Ask yourself this vital question before your next exam. Are your progressive wave answers truly linked to the specific scenario, or are you falling right into the generic trap? Be honest with yourself. Pull out your past papers, look at them. Do they look like Alex's chaotic brain dumps, or do they look like the highly structured, blockbuster answers we built together today? Keep deconstructing, keep evaluating. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.